looking at the effect of the existing substituent on the aromatic ring in terms of whether it's gonna, speed up the electrophilic aromatic substitution reaction called EAS reaction or slow down the EAS reaction. So we look at two examples. One is the methyl group in toluene and the trifluoromethyl group in trifluoromethylbenzene. So we have seen that this methyl group is activating group. The presence of this methyl group speed up EAS reaction compared to this guy, okay? And this guy is a deactivating group. Basically, the presence of this group slow down the EAS reaction compared to the parent, the benzene. Okay? The reason is exclusively impacted by electronic effect here. Okay? So basically, this guy donates electrons to the ring. So what the consequence of the effect of the electron density high on the ring? Because in the rate limiting step, if you see the rate limiting step, the aromatic ring, okay, is a nucleophile react with electrophile, and the rate of this rate limiting step directly, decide the rate of the entire reaction because it's a rate limiting step, a slower step. So now the rate of this step depends on the reactivity of the two, the key species participated reaction. One is the true electrophile, so called E. Okay, the other one is the nucleophile. So if the nucleophilicity of the nucleophile is better, then this step will be faster. And if the nucleophilicity of the nucleophile depends on the electron density of the aromatic compound. Why? Because you see this step, the aromatic compound at the nucleophile is donating a pair of electrons, pi electrons, to the electrophile. So the higher electron density you have on the ring, the more nucleophilic the nucleophile will be. Okay, so that is why you see this guy, okay, is activating group because this methyl group donates electron density to the ring, increase the electron density of the ring, make it more active. And this guy, because fluorine, as one of you said in last class, is the most electronegative element. So each fluorine can steal a lot of electron density away from this carbon. And this carbon has nothing else it can do. It has to steal electron density away from the aromatic ring. So having this trifluoromethyl group will significantly reduce electron density on the ring by the effect of what effect? If you recall learned from last semester. No, that's not. It doesn't have a stereo, but the electron density is not a result of the stereo hindrance. Electron density changes because of inductive effect. Through bound effect, through bound electronic effect, because the virtue of electron activity of the substituents. Here is basically because fluorine is the most electronegative element. So you will steal electron density away from carbon. That's called inductive effect. That makes this carbon very, very electron deficient. So what you can do, my electron was stolen away by those 3 fluorines, so I have steal from, the bond that connect to myself, like basically this aromatic, carbon. Okay. So that's the reason. This is the effect we will, we have, we see here. You're gonna see some similar inductive effect later on as well. Okay. Then we look at the methyl group also is an OP director. Means if you let let's say if you let the toluene, okay, undergo electrophilic aromatic substitution reaction, it doesn't matter what kind of EAS reaction. As long as it is an EAS reaction, the electrophile will preferentially be attached to the ortho position or para position. Okay, and why that's the case? That is mostly judged by the the stability, relative stability of three possible sigma complexes. If you look at the ortho sigma complex, you can see there's a this one. This is ortho sigma complex. Okay, you can write three resonance forms for it, and you have one resonance form where positive charge is on a tertiary carbon that is connect to the methyl group. So because of, if you look at those three resonance forms, all of them are allylic. Okay, but those two are secondary. This one is tertiary. So this form C, is the most stable one, and also this form is the one that is makes the most important contribution in the resonance hybrid. Okay, so the having this form, okay, helps this sigma complex be attain a bit extra stability. Okay, and if you look at the meta sigma complex, you can see all the three resonance forms. They are, look at here, secondary allylic, and the secondary allylic. All of the meta sigma complex resonance forms are secondary and allylic. So meta sigma complex does not receive such a stabilization. And the same argument can be found from the para sigma complex. You do have one resonance form. It's tertiary and allylic. So that makes this resonance form a bit more stable than the rest of the two. So that, because the existence of this form makes the para nitration sigma complex more stable than the meta. So if you look at the potential energy diagram, you see that the ortho para sigma complex both are a bit more stable than the meta sigma complex, because of both of them have the tertiary carbocation character. Okay, makes them a bit more stable. And the para a bit more stable than the ortho, because of para does not suffer stereo hindrance. Ortho does suffer a bit. Okay, and the meta is a bit less stable than both para and ortho. But all those three sigma complexes are more stable than the unsubstituted benzene, because after all, methyl group is an electron donating group. So the increase the stability of sigma complex. Now, and also we can combine the rate and the distribution of the EAS reaction product. We can get the partial rate factor of the toluene, and the partial rate factor of a compound just tell you the relative EAS reaction rate at a single site. So what you can see is also in the para, they are much faster than meta. Okay? But even the meta site, which is the slowest site on toluene, it's a bit faster than the benzene, because the methyl group increase electron density on all the sides of the ring, so makes the all sides rings more reactive than the parent benzene. And then because of also, if you look at the ortho side a bit slower than the para side because of steric reason. Okay, and then a steric reason obviously depends on the size of the existing substituent. If you make it bigger, convert the methyl group to a tertiary butyl group, and the electronic effect, they are pretty much the same, because both cases you have a sp3 hybridized carbon connect to sp2 hybridized carbon. So electronic effect, they are the same, but this guy is a lot bigger. Okay, so the stereo hindrance towards ortho attack is substantially larger. So in tertiary butyl benzene, you're pretty much only getting the para, the substitute product. You're not getting ortho. Now, if you look at the trifluoromethylbenzene, EAS reaction, the key argument I want you to, I mean, I already, discussed with you guys. See, when you have a methyl group connect to positive charged carbon, the methyl group can donate electron to it and make it more stable. But if you have a very powerful electron withdrawing group, trifluoromethyl group, connect to a positive charged carbon, that attachment actually makes this positive charged carbon less stable instead of more stable, because trifluoromethyl will steal electron density away from the positive charged carbon. It will not help the positive charged carbon delocalize, okay? So make it worse, okay? Now, having learned that, then we can look at all the sigma, all the sigma complex of the different nitration product of trifluoromethyl benzene. Now, these are the three resonance forms of the ortho nitration sigma complex. And just like the sigma complex of the toluene, you can write three of them, and the two of them, they are secondary and allelic, okay? And the one of them is tertiary and allelic. But what's different from toluene is that in case of toluene, having a methyl group connect to positive charged carbon, it helps the stabilize this positive charge. But here, this guy is a very powerful electron withdrawing group. So such attachment will actually, what kind of impact will have on the stability of this guy, positive charged carbon? This is a very powerful electron withdrawing group. So you need an electron donating group to stabilize a positive charged carbon if such a group direct attached to it. Now you have very powerful electron withdrawing group. This attachment actually makes this positive charged carbon what? Destabilize, okay? Destabilize, because a positive charge, if you want to stabilize, you want to help it disperse it. So you want to move positive charge somewhere else, okay? But here, this guy tried to attempt to steal electron density away from this carbon. So not only will not help to disperse the positive charges, you actually increase amount of positive charge on this carbon, so it will destabilize. So that's the biggest difference, okay? And you have the similar argument, similar situation can be seen in the para-nitration sigma complex for trifluoromethylbenzene. Basically, you have a resonance form where trifluoromethyl group directly connect to a positive charged carbon. This resonance form will make the sigma complex of para-nitration of the trifluoromethylbenzene less stable, okay? Have this resonance form. Now, if you look at the meta-nitration sigma complex, you can get this all three resonance forms, and every one of them is having a secondary, okay, and allelic carbon. And in all cases, the trifluoromethyl group is not connected to the positive charged carbon. So this guy does not have that, the resonance form give you a hugely destabilized positive charged carbon, okay? Does not, okay? So that means, if you look at the meta sigma complex, okay, meta nitration sigma complex, none of resonance form suffers the destabilization because directly, they have the positive charged carbon attached to CF3 group. Okay, so that means this both ortho and the para sigma complexes. This is ortho sigma complex. Because of this resonance form, you will be destabilized because of CF3 direct attached to the positive charged carbon. Same thing for para sigma complex. You also have this CF3 directly attached to the positive charged carbon. So both these two guys are destabilized. This guy, it does not have such a direct destabilization. So relatively speaking, out of three positive sigma complexes, which one is the most stable one? OPM, which one is the most stable one? Could you? That's one student one answer. Out of 3 sigma complex OPM, which one most stable one? Could you be louder? Oh, very good. Okay, M. Okay, because OP they are destabilized by having one resonance form, like like this one with a positive charge directly connect to the electron withdrawing CF3, and this one positive charge direct connect to CF, powerful electron withdrawing CF3. Those two are severely destabilized by having this resonance form, and this guy, all of them are secondary and allergic, so it doesn't suffer such huge destabilization. Okay, so relatively speaking, M is the most stable one. So the M sigma complex form at the fastest rate, and we know sigma complex formation is rate limiting, so M product form at the fastest rate. So that's the argument. Okay, and if you look at the potential energy diagram, you will see if this one is the formation of sigma complex for unsubstituted benzene. Okay, when you probably can see all of those 3 sigma complexes, they are less stable than a sigma complex formed from the unsubstituted benzene, because CF3 after all is a very powerful electron withdrawing group. Okay, so you will destabilize either directly or indirectly the stability of positive charge. Okay, so all of them are less stable than the sigma complex of unsubstituted benzene. But relatively speaking, meta one is the most stable one out of those out of 3. Okay, so the metas, sigma complex forms at the fastest rate. Therefore, the meta, the substitution product forms at the fastest rate, because sigma complex formation is rate limiting. The second step elimination is not rate limiting. Okay. Now, if you look at the partial rate factor, you will see all 3 sides, the nitration rate, they are much slower than unsubstituted benzene, because unsubstituted benzene is a 1 partial rate factor. Okay, but out of the 3 sides, the meta one is more than 10 times faster than both ortho and the para. Okay, because of the meta sigma complex does not suffer such a huge destabilization. Okay. Now so these are the general. So we discussed both the rate and the visual selectivity of the the one existing substituent on the EAS reaction. So the general rules we have seen will be applicable for all the substituents. If you have electron donating group, you will be activating group, because electron donating group will increase electron density on the ring, makes it more nucleophilic, so EAS reaction will be faster, and it will be also para-director. Okay, and if you have a very powerful electron withdrawing group, it will always be deactivating group, and it will be meta-director. Okay, because of very powerful, the deactivating group, where let's say if you have a very powerful electron withdrawing group, doesn't matter if it's CF3 or not. If you have very powerful electron withdrawing group here, it will destabilize a positive charge if it direct attached to it. Okay, and if you did the practice of all those resonance forms, which I did ask you guys to do, you probably will know for all the OP substitution sigma complex, you will be able to write such a resonance form. Basically, the substituent will be directly attached to the positive charge couple for the O and the P, sigma complex. Okay. So that's why if you have very powerful electron withdrawing group or strongly deactivating one, will be meta-director. All activating group are OP-director. And the halogen substituents, we're going to talk about it later on, kind of special case. Okay. Now let's look at what kind of groups are activating. Okay. So we already have seen that LQ groups activated. Okay. Aromatic group also activating, and if you have alkyl group, means you have a carbon-carbon double bond to the ring, also will be activated. So why these two kind of rings are activating is basically having those two groups attached to ring will help the disperse the positive charge formed in the sigma complex. I'll just give you one example. Okay, let's say assume we have the okay, vinyl benzene. Okay, and let's say we let it react with total nitration. It's easy example. Okay, so assume the rate limiting step, you can have form a sigma complex. You always look at a sigma complex. Okay. And then you can play the resonance form, the okay. Oh, let me see. I will still show the other resonance things, the formal charge stuff. So now what you can see when you have either aromatic group or double bond connect to aromatic ring, if you have the electrophile attached to parasite or ortho side, you will have the positive charge on the carbon on the substituent direct bond to. Okay, so on this side, and then you have extra resonance form you can write. So this resonance form you cannot write for the ordinary substituent. So you can let this pi bond goes to there, okay, and become so obviously this will enable the more extensive delocalization of the pi electrons. Okay, so this is one of reason why double bond is activating group and OP director, and the same reason if you have aromatic group connect to aromatic ring also will be the activating group and OP director. Now the other the substituents, if you notice, okay, the strongly activating, those just called vanilla activating group, they can make it maybe like up to 100 times more reactive compared to parent benzene. And the strongly activating group can make the ring maybe 1,000 times faster, and this one can make the ring like tens of thousands, even hundreds of thousands more reactive compared to the unsubstituted benzene. Now, if you look at all those strongly activating and very strongly activating substituents, what's the common feature? Yes. Yes, very important. Okay, see very good. So that's very the thank you for telling me that. Okay, so all the substituents you have just as the Matt said, all substituent has a atom that carries at least one lone pair, directly bound directly bound to the aromatic ring. That's important. Okay, all of them has an atom that has at least one lone pair. Okay, and that atom directly bound to the ring. Okay, so and to be more specific, all those the strongly activating or very strongly activating, all of them have oxygen or nitrogen, lone pair bearing oxygen or nitrogen atom direct bound to the ring. Okay, and that's actually important. Why they are so strongly activated? Because of oxygen and nitrogen can give lone pair to the ring and increase electron density. Okay, we will see later on. Okay, and the difference, the between let's say very strongly activating and the strongly activating is usually is the very strongly activating one. You have the oxygen lone pair bearing oxygen nitrogen atom bound to ring. On the other end, you won't see anything strongly, won't see any other atom has strong electronic effect connect to it. Okay, but for strongly activating, the substituents, other than having a nitrogen oxygen lone pair bearing oxygen or nitrogen atom bound to ring, other side usually connect to a carbonyl group. And what's the effect of this carbonyl group? We're gonna see, very quickly. Okay, so now carbonyl group. Let's say if you have a substituent connect to carbonyl carbon, so this is the point of connection. So this carbon carries what charge usually? Positive. Okay, I heard someone saying that. Very good. Okay, because of this oxygen is one of the most electronegative element, just less electronegative than fluorine. Okay, so you will steal a lot of electron density away from the carbon. Okay, so that makes this carbon, okay, actually very electron deficient. Okay, it carries partial positive charge. So if anything connect to this carbonyl carbon, almost always will lose electron density to carbonyl carbon. So carbonyl carbon is actually a quite powerful electron withdrawing group. And when we talk about electron withdrawing effect, there are two electronic effect. There are two mechanisms by which a substituent can electronically communicate with other part of molecule. One is something we have seen frequently up to this point called inductive effect, means just through bond effect, by virtue of having the electron activity of the substituents. Like here, if you look at the inductive effect, you can trace back to the high electron activity of oxygen atom. So the electron activity of oxygen is 3.5, so you're going to steal electron density away from carbon. Okay, then carbon become very electron deficient. So what you can do, let's say this is hydrogen, you will steal electron density away from whatever connect to it. So this is called inductive effect. Okay, the other effect we call it conjugate effect, or the resonance effect. So that is basically because you can write because of the delocalization of electrons. Okay, let's say we have oxygen here. Okay, and the connect to the carbonyl carbon. Okay, so yes, inductive effect operate. Okay, so this oxygen can lose a bit of electron density to the carbonyl carbon because of inductive effect. Okay, but there's another effect also is in operation, is the called conjugate effect or resonance effect. So basically what you can see, this lone pair can move to here, become a double bond, And then obviously, if this movement happened, something must be happening here as well. Okay, otherwise this carbon would have 5 bonds connect to it. You know, it's impossible. Okay, so what happened? So this lone pair can go to where? Not lone pair. This bonding pair go to where? The top oxygen. Okay. So this gives us the other resonance form. So if here have something connected, okay, so the left side oxygen going to have a positive charge, top oxygen going to have negative charge, okay. But this is called resonance effect. You know basically also showing that the carbonyl group is an electron withdrawing group, because see, carbonyl group is stealing a pair of electrons from the neighboring oxygen, right? Carbonyl carbon. Because look at here, this oxygen is giving a pair of electrons to carbonyl carbon. So the this carbonyl group is act as a, the resonance, or the conjugate, the electron accepting group here. Okay. So which effect, in this case it doesn't really matter, because of doesn't matter the inductive effect or resonance effect. In both cases, the carbonyl group is the electron withdrawing group. Okay. Now, the thing is a bit different if you have, like those lone pair bearing atom connect to the ring. Let's say here, okay? Inductive effect, if you think about inductive effect of oxygen, this electron withdrawing or electron donating, if inductive effect. Inductive effect is just judged by virtue of electron activity, okay? So oxygen and the carbon, which one is more electronegative? Oxygen, okay? So inductive effect, if you think about it, oxygen here should be electron withdrawing group, okay? However, if you think about the resonance effect, see, the resonance form are right on the right side, showing that the lone pair of oxygen donate to the ring, okay? So as a result of this, the lone pair effect or resonance effect, you have a negative formal charge on the, the ring carbon atom, okay? And if you draw yourself on your paper, don't just look at what I'm doing, okay? You will see that this negative charge can only be found, this lone pair only can be found on those ring carbon that are also or para to the carbon that connect to the OH group. Only, okay? Not on the metal, okay? So if this resonance effect, if you look at resonance effect, OH group is what group here? Donating or withdrawing? If donating, anyone, any different opinions? So it's everyone tell me what's if you look at resonance effect, OH group is what effect? What group? Donating or withdrawing? Okay, louder please. Very good, thank you. Donating, okay? So now Now how do you know which effect, okay, is greater? Okay, because obviously you have two competing. Because inductive effect, when you think of inductive effect, O is withdrawing, right? Resonance effect is donating. How do you know which one is more important? Because inductive effect is purely based on the virtual electron activity. So the higher the electron activity the atom has, the stronger more electron withdrawing gonna be. Okay, and the lone pair effect, the other way around, because of the if less electron active, it will be stronger. Okay, electron donating effect. Okay, but also the other thing, this is very, very important. Okay, the resonance effect is strongly dependent on the stability of this resonance form. Because of this kind of resonance form gives the negative charge to the ring, donate the electron density to the ring. Okay, so the stability of this resonance form strongly impact how much electron can be donated by resonance effect from oxygen atom. So the more stable this resonance form is, the stronger ability the oxygen atom will have to donate its lone pair. So the more stable this resonance form is, okay? Does this make sense to you? The more stable this resonance form is, because this resonance form represents the state where oxygen donates electron to the ring, right? So the more stable this form is, the better ability oxygen can donate its lone pair to the ring. Okay, what determines stability of this form is how strong this double bond is. Okay, if the stronger this CO double bond is, the more stable this form is. Okay, so now is the important part. There's logic and there's conclusion. Okay, for all those lone pair baric atoms, okay, if you have a second period element, okay, bound to the ring, all of them are pretty good resonance electron donating groups. So what are second period elements that could have lone pair? Typically, nitrogen, oxygen, and what? 2 minutes, quiz up. Okay, what are second period elements that could have a lone pair on it? Nitrogen, oxygen, and nobody remember periodic table? What's the other second period element could have lone pairs? Fluorine. Okay, those three they can have a very strong double bond with carbon because the bond is shorter. Okay, the shorter the double bond is, the stronger it is. Okay, so nitrogen, oxygen, fluorine, they can form